Testing, testing, 1, 2. Guten Morgen, ich heiße Leif Beaton. Ich bin ein Solutions Architect von NGINX, and that's all the German you're gonna get out of me. So yeah, I'm here to talk to you guys about different reference models for microservices architectures. Working for NGINX, obviously our approach is more on the network side of things. How do we communicate into a microservices architecture, and how do services communicate with each other? So I'm going to start with a funny slide, because it's important to have a funny slide. But there's a much more sinister truth beneath this one. I do agree with my esteemed colleague here that some things should remain a monolith. Some things certainly shouldn't. This is very easy to relate to. You start with a minimum viable product. Then you get a few customers into your organization. They start looking for new features. You hire a few developers. They develop new features, which in turn leads to new customers that want more features. You get more engineers. And all of a sudden, you have a behemoth of a monolith that's very difficult to maintain, very difficult to update, very difficult to answer the market demands for new features and novelty. What's the solution to this kind of a problem? Transition. Moving into a modern application architecture. So you go from the monolith, where it is appropriate, into a more DevOpsy attitude, cloud native, which is obviously a very popular term. So you start with small, loosely connected services. You have a DevOps culture, so the teams actually function as a cohesive unit rather than siloed approach, which is typically the traditional approach. You have continuous delivery into anything, into bare metal, into VMs, into containers, or even functions. You finally get to see infrastructure as code. And you do that using typically lightweight programmable interfaces, REST, JSON, etc. Now, give me a few seconds just to talk about who we are, so it puts things into context for the rest of it. NGINX started as a web server a long time ago. It was written as a response to the problem Apache was having with the 10,000 concurrent connection problem. So we transitioned from that kind of architecture, kernel scheduled threading model, into an event-driven architecture, which was able to respond to a multiple of the 10,000 concurrent connections Apache was handling at the time. Since then, we've grown quite exponentially. We are many more things. Our marketing department has taken to lovingly call NGINX the Swiss Army knife of the internet. And while I don't agree with marketing speak most of the time, that's actually quite accurate. We are still a web server. We're also a load balancer, a reverse proxy, a caching solution, a single sign-on solution, TLS termination, etc., etc., etc. The list just goes on and on. So we're clearly quite invested in the networking side of things and how do we communicate. Now, you'll hear me talk about customers sometimes in the presentation. Forgive me for that. That's just me being damaged by working in a sales organization. Think end user whenever I say customer, okay? Deal? Good. So let's talk architectures. For this slide, which I've called the present and the future, I'm talking about three distinct reference architectures. There is a fourth as well, the simplest one, the proxy model, but it's so similar to a monolithic approach that it doesn't really require any explanation. You have a perimeter ingress controller into your microservices architecture, and that's it. So it's semantically very similar to the router mesh model you see all the way to the left, with the exception that the router in the midst of your containers is not there. So, the router mesh. We do the same as in the proxy model. We have an ingress controller at the perimeter of your microservices architecture, but we also add a router in the midst of your containers. So instead of the containers communicating directly towards it, with each other, they will communicate through the router. What benefits do I get from that? Well, you can set policies on the communication that happens between the containers. You can set rate limiting, authentication, authorization, these kind of things, and you can centrally manage that rather than having to hard code it into each and every container. Container/pod. It says Kubernetes here, but it's by far not the only orchestrator. It's just the most commonly known one, so I use that in the slide. Next, we have the per service proxy, or as we historically called it, the fabric model. In the fabric model, we attach a proxy into each and every container or pod. Every microservice will only ever talk to localhost. The sidecar proxy on the container picks up on that communication and deals with it according to your wishes, however you want to communicate to the other containers. What benefit do I get from that, I hear you asking? Good question. Well, if you need to secure the communication between your services, it's very inefficient to do so without some kind of strategy. Because if you don't, there will be 8 to 13 messages happening between the containers, establishing a secured protocol for each microcommunication. It'll do the microcommunication, then terminate the secured protocol, and 2 nanoseconds later, the exact same process repeats. By doing this, having a sidecar proxy, we can keep those established secured protocols in place, keep them alive, so consecutive requests going between containers will happen over an already established secured protocol. Studies we've done find that that approach, if you need to secure the communication, is about 80% more efficient. Why would you need to secure that? I mean, all of these microservices are going to be internally on your network, right? Well, that is true, but there are security considerations to take into effect. A monolithic approach, any transaction that happens in your monolith is a function call within memory. That data is relatively secure in transport, relatively. In a microservices architecture, all of these requests are happening as a network call. It makes it infinitely less secure, so securing it in some way might be appropriate. Now, the per service proxy, it looks oddly similar to a service mesh architecture, I hear you say. Didn't I? Yeah. That is correct, but it's missing one component, and that's the future bit of the slide here. It's missing the control plane, and the reason you would want that in that scenario is once you start having a sidecar proxy in each container, it becomes a very daunting task to manage that, to make sure all your routing is set up correctly, manage your certificates, all of these things. Just knowing how your topology looks can be a challenging task. So let's talk about what is a service mesh. So a service mesh is an invisible autonomous layer 7 routing layer for distributed multi-service applications. That's a mouthful. So yeah, it's most commonly implemented as a sidecar proxy, as we saw in the previous slide. There are some implementations in the marketplace right now. Istio is the one that's banging their drum the loudest, but there are others as well. So you got Console Connect, Linkerd2. We had an early implementation we called Engine Mesh. And a lot of other players are working to make a solution in this space, including us, I might add. So customers come to us, end users come to us, and they say, we need a service mesh. When they do, we start thinking about where are you in what we call the maturity journey, and where are you heading? Where do you want to ultimately end up? What we find as step one is when you have early production applications, established apps. The applications are simple, they're well-defined, well understood. This is a very typical model when you have a monolith, but you're containerizing that for scalability and for replication purposes. In this case, do I need a service mesh? No, not really. Kubernetes native tools does this brilliantly. Service discovery and scaling, load balancing and health checks, access control, and ingress load balancing. These are all Kubernetes features, and other orchestrators as well, for that matter. So what do we do with these people? We do the ingress control. So we substitute the native Kubernetes ingress control for our solution. I might add the native Kubernetes ingress controller is actually NGINX based, small tidbit. And we rely on Kubernetes for the majority of the rest of the bits and pieces, because there are good tools inside Kubernetes. Okay, customer says to me, well, Leif, you don't understand. My application is a little bit more complex than that. And if it isn't already, it's going to be. There are business critical applications, multiple distributed components, changes are frequent, and we need more control, and not least of which we need more visibility. Now, surely I need a service mesh. Not really. Kubernetes itself cannot do all of this for you, but Kubernetes, with a little help of their friends, namely us, can do that. We can take care of mutual TLS, we can take care of metrics and tracing, and we can take on the proxying tasks for load balancing and other things like rate limiting, access control, and traffic management. So that looks like pretty much like the second model we saw in the earlier slide, where we have a router in the midst of the containerized strategy, and we can also pick, if we need to, elements from the fabric mesh. So if individual containers require a sidecar proxy, we can do that without going full service meshy, to construct a word. This is the pattern that we see in the vast majority of the people we deal with. This is where most of them find themselves. The customer then tells me, "Yeah, Leif, you still don't understand. Our applications are much more complex than that. If you have diverse application stacks, if you have frequent and hard to control changes, then all of a sudden you might be a candidate for service mesh. The service mesh will take care of all of the magic features. It will intercept all of the network traffic for each and every service. It will magically inject TLS. It will take care of metrics and tracing and all of the good layer 7 stuff as well." So that looks a little bit like this, and that's our future model. We're not quite there yet. We have a controller, which is a centralized control plane, which will, in the immediate future, get a component for service mesh. We do everything you see there, except for the missing box on top with the control plane. That's where controller comes in at a later stage. We have these solutions in the wild. We have delivered this to customers already, but it is quite an undertaking to control a service mesh without having a proper control plane. So service mesh addresses limitations in a different way. So we've already talked about the sidecar proxy, and that is the most typical model for a service mesh. We've talked about the additional operations that a service mesh can do in terms of mutual TLS, monitoring, tracing, and traffic management. And yeah, typically, no application code changes are required because you take care of all of these things at a centralized tier rather than in the code for your services. Now, there is a tipping point, and we'll see a graph shortly, of where the benefits of a service mesh outweighs the cost of deployment. There are two costs to it in a basic sense. It's the learning curve, obviously, but there can also be a capital investment cost in going the service mesh route. It invariably adds complexity. There's a latency issue that needs addressing as well, potentially. There could be instability due to more moving parts. It provides generic services, so it may not necessarily be a direct replacement for the native ones in terms of metrics, for instance. Not to mention that the metrics may be different for different implementations. A lot of the vendors we see right now are doing, not necessarily intentionally, but they are ending up locking you into an implementation as it stands. So it's a sliding model. On the other hand, there are benefits to a service mesh as well. Once you reach that level of complexity within your microservices implementation, a service mesh brings tremendous value in terms of being able to solve some otherwise almost impossible problems. At that level of complexity, doing things like blue-green deployments or canary testing and automating that, having rollbacks in place and so on and so forth, is incredibly difficult, if not very near impossible. Yeah, cascading within an app as well, without having a proper centralized and automated structure to control that traffic, becomes a big, big issue. So I promised you a graph. Here it is. This is very, very close to the truth as we see it when we talk to customers. Towards the left, simple applications, all the way to monoliths, and then simpler microservices implementations, going all the way over to the right, where you have much more complex interoperability, many microservices, perhaps many segments of microservices that need to communicate with each other as well. The further you are to the left, the less benefit you're going to see of a service mesh in terms of cost. The further you are to the right, that becomes inverse, because the cost of maintaining that with orchestration, traditional orchestrations like Kubernetes or Swarm or Mesosphere or anything like that, rises, while the cost of implementing service mesh is relatively flat in curve. So there's a tipping point. It's a bit to the right, but that tipping point has a tendency to move towards the left of the scale as your application grows in complexity. So if you're, well, you'll typically start somewhere on the left. That's where we see the start of the microservices journey within companies happen. And as you progress towards more complex infrastructures and applications, that tipping point tends to gravitate towards the left as well. It's also, we typically tell customers that it's a bit early days for a service mesh implementation. The definition isn't solid yet. As Fabrizio mentioned earlier, very recently the conversation about microservices was, what is a microservice? Today we have a little bit of a broader understanding of it, but the same thing is true for newer things. So service mesh, what is it exactly? Where does it fit? Do we need it for everything? So that's our 3 reference architectures, and at this stage I'll take questions. Thank you.
Hi, just a comment. Is it possible that one of the disadvantages of having like a control panel is that you add a single point of failure to the system, while we want like a distributed application that is avoids single points of failure?
That is a brilliant observation. That is true in a lot of architectures, and a lot of providers suffer from that exact problem. And they generally do that because they bolt the control plane directly onto the data plane. That is not a particularly good approach in our opinion, because you do that, you introduce that single point of failure, but you also handle control plane tasks at the data plane, meaning that you're also suffering in a performance perspective. Our approach to the centralized management and monitoring solution is completely decoupled from the data plane. So even if the building that your NGINX controller is in detonates, it catches fire, the machine is stolen, something or other, the data plane is not affected at all. The traffic will continue to roll. You're missing monitoring, and you're missing implementing changes, but the infrastructure as you know it right now will continue to function. Does that answer the question?
Well, partially because I think the interaction and to have a control plane at the data plane level adds functionality, so you can really control and be more dynamic in your decisions where the flow needs to go. So there is a trade-off, I guess, there, and well, it's up to explore which side probably a lot of applications will go. Probably a lot of applications will still want to control and have like the flow at the data plane level. So yeah, well, we'll see.
Yeah, no, you are absolutely correct. There is a trade-off involved, and that's always going to be the case as you add complexity, you add more moving parts. There is more that needs to be governed. I work for NGINX, so I kind of have to say this, but I honestly do believe that we have a very wholesome approach to this, to that side of things. In the complete decoupling of the control plane for one, so there's no performance impacts, and there's also no instability if the control plane disappears temporarily. But there are other elements as well. A proper control plane for a service mesh architecture in particular should have built-in magic. There should be unicorns and there should be rainbows, because it needs to be able to help you understand what your topology is. Because when the architecture becomes that complex, your theory of what your topology is isn't necessarily exactly the same as what it actually is. So having a system that can help you figure out, okay, these services do not communicate at all, so we don't need to have a route between them, even though it logically looks like they would be communicating. It needs to be able to measure these things and make suggestions based on, well, effectively unicorns and rainbows.
Any more questions?
I enjoyed your taxonomy with the maturity levels. Right?
Thank you.
Starting at level 1. But you seem to be assuming that there is no microservices architecture without a Kubernetes cluster?
No, yeah, this slide isn't excellent from that perspective, and I apologize. There absolutely is, of course. I mean, the microservice doesn't even necessarily have to be in a container as it stands. There is also serverless, as was talked about earlier. This is just the way I stole this from another slide I use when I talk to customers, and Kubernetes is more or less the de facto standard that we come across when it comes to orchestration. So that's why it looked like that. My apologies for the confusion. Cheers. Any further questions? Well, you get an exercise today.
What about the stateful applications for service message?
In terms of what?
Replicated databases, for example.
Yeah. There is a requirement for state still. Now, we've all been living under the mantra that no application should be stateful, etc., etc. But yeah, there are applications where that will have to be part of the equation. We and others like us offer session persistence and ensuring that communication that originates from source A with fingerprint B will always go to service replica C. So we can deal with that, we can handle that already. Implementing that in a service mesh is obviously quite tricky, because you have to distribute these settings onto a lot of different systems. But yeah, we can deal with that. Cool.
So
well,
let's thank the speaker again.
Yeah, I think thanks so much.